So in this episode, we're going to talk about index monitoring. So let's go ahead and create a table with an index. Create table layout as select row num row number o dot star from DBA objects. Let's create an index on that table. Create index on let's gather some statistics. Exec dbs stats dot gather table stats. Now let's see if an index is being used. Select row number is equal to 20,000. Select. Let's look at the explain plan. Select star from table dbms explain cursor. And we can see the index is being used. Let's look at this particular view, $object usage. This is the table where you would look to see if an index is being used and monitored, and in this case it's not. The key thing to note about $object usage is that there is no owner column, so you actually have to be logged in as the object owner or the index owner to see whether rows appear in this particular view. So in this case, our owner of the table and index is sys. So we're going to turn on monitoring, and how is that done? Well, it's this way. Index, index, monitoring usage. Now let's run our query again. And it's going to use the index. So let's look now at select $object usage. And we can see that the usage is yes, the monitoring is turned on, and the usage is yes. Now let's turn it off. Turn off the monitoring. Alter index no monitoring. Usage. Now let's look at select star from $object usage. We can see that the table and index is still there, but monitoring is turned off. If we drop the object, like drop the table or drop the index, this particular row actually disappears. Let's go ahead and drop the index. Drop index, perch. And then, oops, drop index, Soleo index. Now let's look at $object usage. And we can see the object is now gone. And that's the point of this particular episode. So today we're going to talk about reverse key indexes. Reverse key indexes are used to reduce header contention. Here's the scenario. So you have a table with the primary key based on a sequence number. The sequence is in sequential order. So as you insert a record, it's going to go into a block, one particular block. As you insert the next record, it's probably going to go into the same block. If you have a lot of users doing a lot of inserts, there's going to be contention for that last block. So the solution is to put the numbers in reverse order so that each insert will then fall into different blocks. That's the good news. The good news is it will reduce that header contention. The bad news is that now queries based on a range will be impacted because now the numbers are no longer in sequential order, and so it can't do an index range scan very effectively. So, But that's usually not a problem with, say, a primary key, because we're usually looking up something by primary key as in quality. We're going to look at one particular record. We're not going to look at a range of records. So let me show you some examples using reverse key indexes. The first thing I'm going to do is, let's make sure my table is dropped. I think it is. Okay, let's create a table with a regular index. Here's the table. Here's the index. Let's look at the index type. In this case, the index is a regular old index, a sequential index. It'll say normal, and I'll show you what it looks like when we do a reverse. But right now it says normal. Let's gather our table stats, and then let's run a query. In this case, we're going to run a range type query. So I want a range between 20,000 and 20,001. We look at the explain plan, and we can see that there's an index range scan using the index that we created. Now I'm going to recreate this index with the reverse option. Now let's look at the index type in DBA indexes, and now we see that it says reverse. Let's gather stats and run the same query as before. And let's look at the explain plan. And see, now we can see we're using a fast full scan rather than a range scan. That's because the numbers are no longer in sequential order. So the next thing I want to do is let's rebuild this index. Oh, okay, sorry. Let me just show you this. Is that typically this isn't a problem. This could be a problem, but in the case of a primary key, typically it's not a problem because we're usually looking up something by inequality. So let's do that particular query. Okay, I'm looking up one record, and let's look at the explain plan. And I still use the index, but now because I'm just looking up the one record, so that's not impacted. So let's go ahead and do a rebuild. And what I want to show you here is that now I've taken the reverse key index and do a rebuild, but I want to show you that when you just do a simple rebuild, that doesn't change whether it's reversed or not. So it was reversed, I did a simple rebuild, it doesn't convert it back to a normal index, it stays whatever it is, either normal or reversed. So to get it to be non-reverse, if I wanted to go back, we have to actually explicitly say no reverse. And now it's normal. And that's it for this particular episode. So today we're going to look at some compressed indexes. Compression of indexes is not like a zip file. What we do here is we actually eliminate some duplicate entries that are in the leaf blocks, and thereby making the index much smaller. And by making the index much smaller, then each I/O, or the I/O necessary to do a full index scan, is reduced. So let's take a look at some examples. So the first thing I'm going to do is drop an old table. It's there. And let's create in this case, I'm going to create an index on the owner, object type, object name, and sub-object name of DBA objects. Then I'm going to take the default, alter the index, and say rebuild compress. And what happens when we say compress with no number? In a non-unique index, it tries to compress all of the columns in the index. But when you use a unique index, it does n-1, the number of compressions. So in fact, let's prove that by looking at the prefix length column. So you can see we have 4 columns in our index, but our prefix length, that is the number of columns that we've compressed, is really just 3. We can also specify the amount of compression that we want. So in this case, I did a alter index, rebuild compress 2, and we could show that the prefix length is now 2. But if I said, and again, if we try to do more than that, if we try to do, say, compress 4, try to compress all of the columns in a unique index, it will fail. So let's take a look at that. And sure enough, we do. If this was a non-unique index, we could do a compression of 4, but this is not, so we can't. And finally, you can go back and say rebuild with no compression whatsoever. And when you do so, the prefix length becomes null. Let's take a look at that. So the real question is, when you have an index that has some various duplicates in it, what's the optimal compression? And the answer is that Oracle will tell you. So let's do an analyze index validate structure. And let's look at the index stats. Stretches that a little. So in this case, what it's telling us is that the optimal compression is 2, and that we can actually save 28% of our space. And let's see if that's true. I'm going to say compress 2. Then I'm going to look at, we're going to say, oops, oh yes, we can prove that the compression is now 2. Let's analyze the structure, and then and in this case now we can see that the space is now about 71% of what this was, or 72% of this, which is spot on with what it told us in terms of the optimal compression. So to find out, to summarize here, to find out the optimal compression, we just do a validate structure, alter index, index name, validate structure, and it will give us some advice on how to do, or how much compression we should do. And that's it for this particular episode. So today we're going to talk about invisible indexes. You can create an index or alter an index to be invisible, and that allows you to do some what-if analysis to see the impact of what this index does to the application. So you can keep the index in the database, you can keep it consistent, but it just won't be used in the explain plan. And if you create a very large index, you can see whether it's actually being useful or not, in which case you can drop it or just not have it or add it back. So it gives you a lot of tools to do some what-if analysis. So let's go ahead and show you how this works. I'm going to create a table with an index. Just created the table. I'm going to add the index. Now I'm going to gather stats. And let's do a query, and I want to show you that the index is actually being used now. See that the index is actually being used. Now let's make this index to be invisible. When we do so, you'll see that in DBA indexes there's a column called visibility. We can see that now it's invisible. So the index is still there, but if I run a query and look at the explain plan, it's not going to be used. Now I'm using the full table scan, even though that index is there. So great, but there's a few other things we can do. So in this case, I altered the index to be invisible, but now I'm going to show you that I can do the same thing by just creating it outright. So let's go ahead and drop it, redo my stats. I'll show you that now I'm using a full table scan and I have no indexes whatsoever. Okay, great. So I'm doing a full table scan. Now I'm going to create the table create the index as invisible to start with. So you can see that syntax. We can see the visibility is actually invisible. Let's go ahead and gather stats, even though the index is there and it's invisible, it will never be used. So let me show you that. So now I'm going to run my query and my explain plan, and I'm still doing a full table scan. So even though you have an invisible index, you can run the query again, this time using the hint saying use invisible indexes, and now, lo and behold, now we see that it's using an index scan. And that's it for this particular episode. Hello, in this segment we're going to talk about IOTs, or index organized tables. What is an index organized table? Well, instead of a table being constructed as a heap table, it's constructed like a B-tree index. So what's the advantage of having an index organized table? Well, if you know your queries are going to mostly use these indexes or this index structure, then it can save you some space and some I/O. It can save space because there's only the index segment here and not the underlying table. And it can save I/O because consider how how a traditional query works. It first traverses the index, gets the row ID of the underlying table, goes to the table, and gets the data. In this case, we have no underlying table, so we save some additional I/O by just traversing the index segment itself. So what are some of the restrictions and some of the options? Well, the first most important restriction is that IoT must have a primary key. When we create the primary key has to be, or when we create the table, the primary key has to be within the DDL statement itself. You can't create the table and then alter it later to create the primary key. The primary key has to be within the data definition language of the table itself, and we're going to talk about that. There are three options, important options or clauses: the overflow clause, including clause, and percent threshold. The overflow clause allows you to specify an overflow segment. So some of the columns that are in this particular table are going to be well used, and those that are not well used can fall into the overflow segment, which is itself a table segment. So only the few columns that need to are in this index segment. The including clause allows us to specify which columns go into the index block and which columns go into the overflow segment. And finally, there's the percent threshold clause, which allows us to specify the percent, how full the index block is before it starts using the overflow segment. So let's look at some examples. Here's an example where we create a table. It's organized index. This is how you specify an IoT. It has an inline constraint without a name, so it'll be a system-generated primary key. And this is a very typical type of IoT, so let's go ahead and create it. The next example, we use an out-of-line constraint, so we can specify the primary key name and specify which columns can be are part of the primary key. We indicate that it's an IoT. We're going to create an overflow segment, and we're going to say including Y, which means that Y and all the previous columns, in this case just X, will be in the index segment, and Z will fall into the overflow segment. Here's another example with a out-of-line constraint. It doesn't have a name, so it'll be system-generated. It's an IoT. We have the compress option, which means that the first two columns of the primary key will be compressed, and percent threshold of 50%, so that when the index block itself gets to be 50% or more, or actually more than 50%, then the remaining columns will fall into the overflow segment. In this particular case, I just wanted to show that we can create a table and specify the table space for the table itself, but the overflow segment can be in a different table space. After we created this table, we can actually move the table spaces. Even though this is an
the underlying data structure of this table is really an index, we still say alter table move as opposed to alter index rebuild. So we do alter table move, and we can move the table space of the table, in this case the index segment of the table, and we can also move the overflow table space as well. So let's do that. You can also create a partition table. And so in this case, we've created an out-of-line constraint, and it's an index organized table. And this is pretty standard partition syntax here. But the point is we can create an IOT that is partitioned. So in this case, we're going to create an index organized table. We're going to put it into table space users. The percent threshold is 20, so anything above 20, any index block that's above 20, the remaining columns will fall into the overflow segment. The including description clause means that the description and the previous columns, in this case ID, will fall in the index block, and then map will fall into the overflow segment. We have a constraint primary key here of ID. So let's go ahead and create that. Okay, let's take a look at what our system tables tell us about this particular table. So the locations table is found in user tables, and it is labeled as an IoT type. Let's take a look at the indexes that are created. In this particular case, we're going to see two indexes. One is the primary key, or in this case, this is the table itself, the IoT, and also because we have a blob, there is a blob or a lob index as well. To find the overflow segment is a little tricky. The first thing you have to do is actually find the object ID of the table. So let's go ahead and do that. In this case, this was a previous example, but in this case, our object ID is 82892. So 82892. So now we want to find, let's go ahead and find the overflow segment associated with that. So we go select name, and notice that there is an overflow segment created. The IoT type is IoT overflow, as opposed to the IoT top. This is the actual IoT itself. This is the overflow segment, and the name of it is sys_IoT_over, and the object ID of the table name itself. Now let's look at the segments, and I'm going to have to type this one out, so let's do that. Actually, let's do this. Okay, so our table segment is located in table space users. Our lob segment is in also table space users, and our overflow segment is in table space Soleo. So let's move each one individually. So now let's do alter table locations, move table space Soleo. Notice that now we've moved the table to Soleo. Let's go ahead and move the overflow segment. Alter table locations, move overflow space. And notice that now we've moved the overflow segment to users. And now finally, let's move the lob segment. And that syntax is a little tricky, so let's do that. Copy that. Here's actually the syntax for that. And you can see that we moved the lob segment now, or the lob index actually, from users to now Soleo. And that's it for this segment.